Imagine a lighthouse so powerful that its beam crosses the darkness between stars. Now imagine that the lighthouse is not on a shore, but inside a nebula, spinning hundreds of times every second. This is the strange world of a pulsar, and new observations from NASA's Chandra X-ray Observatory and the imaging X-ray Polarimetry Explorer are revealing how one of these objects shapes the space around it. The object is a pulsar embedded in the Lighthouse Nebula, a cloud of energized gas and magnetic fields in our galaxy. Recent studies combine X-ray images with polarization measurements, giving astronomers more than a picture of where the radiation is. They can also study the direction in which the X-rays vibrate, a clue to the invisible architecture of the pulsar's magnetic field. To understand why that matters, we need to begin with the death of a massive star. When a star many times heavier than the Sun runs out of fuel, its core can collapse in a fraction of a second. The outer layers explode outward, while the center is compressed into an object roughly the size of a city. That object is a neutron-star. It may contain more mass than the Sun, yet fit inside a sphere only about 20 kilometers across. A teaspoon of neutron-star material would have an astonishing mass on Earth, because the star's gravity has squeezed atomic matter into an ultradense sea of neutrons. Some neutron stars rotate incredibly fast. As they spin, their magnetic fields sweep through space like beams from a cosmic searchlight. If one of those beams crosses Earth once during every rotation, our telescopes detect a pulse. That is why these objects are called pulsars. The pulsar in the Lighthouse Nebula is not simply flashing in empty space. It is feeding an enormous bubble of particles and radiation, called a pulsar wind nebula. Electrons and positrons are accelerated to energies far beyond anything produced in an ordinary laboratory. They race outward along magnetic structures, lighting up the surrounding cloud in X-rays and other forms of radiation. Chandra's images show the large-scale shape of this energetic environment. The nebula has a remarkable, directional appearance, with luminous features that resemble a beam or a wake. The image is not a photograph in visible light. It is a map of some of the most energetic events taking place in the system. But an image alone cannot tell us exactly how the magnetic field is organized. That is where IXPE changes the investigation. Its detectors measure X-ray polarization. In simple terms, polarization records a preferred orientation in the waves of light, like the alignment of ripples on a pond. X-ray polarization is difficult to measure because the signal is faint and the source is incredibly distant. Yet when a pattern appears, it can reveal whether high-energy particles are moving through an ordered field or a chaotic one. It can also show how the field bends, twists, and guides the particle wind away from the pulsar. The results suggest that the bright structures of the Lighthouse Nebula are closely connected to the pulsar's magnetic geometry. Instead of behaving like a random explosion, the outflow follows channels carved by fields and pressure. The nebula becomes a natural laboratory for plasma physics under conditions that cannot be recreated on Earth. Picture the central neutron star as a rotating engine. Its spin energy is gradually transferred into the magnetic field and then into the particle wind. The energy does not leave uniformly in every direction. It is shaped into streams, arcs, and shock fronts, where particles abruptly change speed and direction. At those shock fronts, particles can gain extraordinary energy. They may then spiral around magnetic field lines, emitting synchrotron radiation. This process produces the glowing X-rays that Chandra sees, while the polarization carries information about the field lines themselves. The word lighthouse is especially fitting because the system has both a rotating source and a narrow-looking direction of emission. But the nebula is not a simple flashlight. Its appearance depends on our viewing angle, the shape of the magnetic field, the density of nearby gas, and the history of the supernova that created the neutron star. Even the apparent beam may be a moving structure rather than a single rigid ray. As the pulsar rotates, the wind can form a spiral or a series of shock features. Light from different parts of that structure reaches us together, creating a composite image that looks almost architectural. This is one reason polarization is so valuable. Brightness tells astronomers where the radiation is strongest. Polarization helps tell them why it is strongest there. Two regions can shine with similar intensity while having completely different magnetic arrangements, and IXPE can help distinguish them. The observations also connect this nearby cosmic scene to a much wider question: how do compact objects transfer energy into their galaxies? Pulsars are small, but their winds can influence a volume of space many light-years across. They inject particles, magnetic fields, and radiation into the interstellar medium. Over time, those particles may travel far from the original star. Some contribute to the population of energetic cosmic rays in the Milky Way. Others interact with gas and dust, changing the chemistry and temperature of their surroundings. A stellar remnant can therefore act as a long-lived engine after the original explosion has faded. There is another mystery hidden in the data. Neutron stars are governed by physics at extreme density, where matter is compressed beyond the structure of ordinary atoms. By measuring their spin, magnetic behavior, and energy loss, scientists test models of matter under conditions that exist nowhere else nearby. The pulsar's rotation is not perfectly constant. It gradually slows as energy escapes through the wind and radiation. Occasionally, a neutron star can also experience a sudden change called a glitch, as its interior adjusts. Each change offers another clue about the hidden layers beneath the crust. The Lighthouse Nebula is therefore more than a beautiful object. It is a record of a stellar death, a map of relativistic particles, and a test of theories about magnetic fields. Chandra and IXPE are looking at the same system with complementary senses. One emphasizes structure and brightness, while the other reveals orientation. This combination is part of a new era in X-ray astronomy. For decades, space telescopes mainly counted X-ray photons and located their sources. Polarimetry adds a new dimension. It is like moving from a black and white outline to a map with arrows showing the flow of an invisible wind. The technique may eventually be applied to more pulsar wind nebulae, supernova remnants, active galaxies, and black holes. Each target can answer a different question about how nature accelerates particles and organizes magnetic energy. The larger the sample becomes, the easier it will be to separate universal laws from the quirks of one object. For now, the Lighthouse Nebula gives us a particularly vivid demonstration. A dead star, compressed into a city-sized sphere, continues to pulse and pour energy into space. Its magnetic field reaches outward, sculpting a glowing nebula that appears calm only because we are observing it from an immense distance. The next time you look at a star field, remember that some of the quietest-looking points may be spinning engines. They may be launching particles at nearly the speed of light, building shock waves, and tracing magnetic patterns across light-years of darkness. The universe does not need a visible shoreline to make a lighthouse. It can build one from a collapsed star, a magnetic field, and the remains of a supernova. And with X-ray observatories capable of seeing both the shape of the light and the direction of its vibration, we are finally learning how that cosmic beacon works. In the deep silence between stars, the pulse continues. Once each rotation, the beam sweeps past the universe. Once each observation, another piece of the hidden structure becomes visible. The Lighthouse Nebula is not merely shining into the dark. It is showing us how the dark is organized. The color choices in a public image can make this violence look almost gentle. Blue regions may represent the highest energy X-rays, while gold or red tones can mark other energy bands or different particle populations. These colors are scientific translations, not what human eyes would see, but they help us compare the layers of the nebula. Behind every pixel is a long chain of work. The observatories collect individual photons, each carrying a tiny clue about the source. Researchers remove instrumental background, account for detector geometry, compare energy ranges, and test whether the apparent polarization is truly coming from the nebula rather than from the telescope itself. That care is essential because a false polarization signal could lead to a false picture of the magnetic field. Independent observations and detailed modeling are used to check the result. When the image, the spectrum, and the polarization all point toward the same physical story, confidence grows. The story also has a time dimension. Because the nebula is several thousand light-years away, its light began traveling toward us long before modern astronomy existed. We are seeing an ancient event in the present, and every new observation samples a different chapter of that history. If the pulsar wind changes, the nebula can respond. Bright knots may move, shocks may brighten, and the pattern of energy may shift. Repeated observations allow astronomers to make a kind of time-lapse movie of a relativistic environment, tracking changes that unfold over months or years. These changes can reveal how quickly particles escape and how efficiently magnetic fields convert rotational energy into radiation. They also help estimate the age and evolution of the system. A nebula is not a static monument left behind by a supernova, it is an active ecosystem powered by the compact object at its center. The same physics appears on larger scales around young stellar objects and black holes, although the sizes and energies differ. In each case, magnetic fields can channel matter into jets, create shocks, and turn motion into light. The Lighthouse Nebula gives astronomers a relatively close and sharply defined example of a process repeated throughout the cosmos. Future X-ray missions may improve the polarization map, resolve smaller features, and observe more of the pulsar's spectrum. Radio telescopes can trace the magnetic field through polarized radio emission, while optical and infrared observatories can study dust and cooler gas around the energetic core. Together, these wavelengths create a multi-layered portrait. X-rays show the fastest particles, radio waves can reveal older populations of electrons, and visible or infrared light can expose material shaped by the original explosion. No single telescope sees the whole story, but each fills in a different part of the map. There is a lesson here about scale. The engine is only city-sized, yet its influence extends across a region larger than our entire solar system. A small object can dominate its surroundings when it rotates rapidly, carries an intense magnetic field, and releases energy with extraordinary efficiency. That contrast is one of the most compelling features of neutron stars. They are physically tiny but conceptually enormous. Their surfaces may be solid in a way unfamiliar to us, their crusts may crack under stress, and their interiors may contain forms of matter that remain subjects of active debate. Every pulse from the Lighthouse Nebula is therefore both a signal and an experiment. It tells us about the external nebula, but it also carries information about the unseen star. By comparing the timing, energy, and polarization of the radiation, scientists can constrain what the neutron star is made of and how its magnetic field is anchored. The work is not finished, and that is precisely what makes the observation exciting. A new map can solve one mystery while exposing another. A surprisingly ordered field may require a better explanation for how turbulence is suppressed, while a chaotic region may reveal where particles are being accelerated most efficiently. Science advances by following those mismatches. The Lighthouse Nebula becomes more than a finished picture, it becomes a question written in light. How does a rotating remnant maintain its beam? How far do its particles travel? And what happens when the engine finally loses enough energy to fade? For millions of years, the nebula may continue to evolve. Eventually, the pulsar will slow, the wind will weaken, and the glowing bubble will merge into the surrounding interstellar medium. But the particles it released may keep moving, carrying a faint memory of the star that launched them. Today, we catch that memory as X-rays, as a polarized pattern, and as a luminous shape resembling a lighthouse suspended in space. It is a reminder that cosmic catastrophes do not always end in darkness. Sometimes, they leave behind a beacon that teaches the universe's deepest physics one photon at a time. In the deep silence between stars, the pulse continues. Once each rotation, the beam sweeps past the universe. Once each observation, another piece of the hidden structure becomes visible. The Lighthouse Nebula is not merely shining into the dark. It is showing us how the dark is organized.